Good morning, everybody, and welcome to this third and fourth sessions on money-body perturbation theory. And the topic today is first a continuation of the exercise or example, as we also called it, from last week. And this was an example of a simplified problem which we could solve analytically. And this will serve as a demonstration of both Brane-Wigner perturbation theory and Rayleigh-Schrödinger perturbation theory. And there are going to be contributions to Rayleigh-Schrödinger perturbation theory, which we need to interpret. And we are going to interpret these contribution in terms of a diagrammatic representation. And that is going to lead to the next topic. So we will first just finish the example and get the expressions. And then we need, since diagrammatic representation is widely used in money-body physics, we need to discuss the rules for diagrammatic representation, which means the diagram rules. And we are going to encounter some subtleties, which often can lead to some confusion, and that is about linked and unlinked diagrams. So this is a technicality, and this leads also to something which is called Pauli violating diagrams and the final link diagram theorem, which states that the only contributions we need to take into account when we are using Rayleigh-Schrödinger perturbation theory is the so-called contribution from linked diagrams only. So we are going to spend today and tomorrow on these diagrammatic technicalities. And one of the reasons for that is that these features, they appear also in other money-body theories like couple cluster theory and Green's function theory, and money-body methods in general, which base themselves on a diagrammatic representation. And diagrams are a very powerful way of expressing contributions in money-body theory. Moreover, from tomorrow, you will also find the second midterm, and I suggest a deadline for Monday, the 18th. If you need a little bit more time, this is something which we can always be flexible with. Finally, the material which you will encounter this week is material which is not included in a written form in my lecture notes, so this will mainly be through whiteboard lectures. But everything which I cover is taken from chapters 5 to 7 of Sherritt and Bartlett. Chapters 5 and 6 are those which include many of the technicalities I will discuss today. And chapter 7, as well as tomorrow, and chapter 7 has more a discussion on the technicalities on how to efficiently calculate contributions to money-body perturbation theory. So chapters 5 and 6 are those which deal with the diagram rules, and also these chapters have a pretty in-depth discussion of linked and unlinked diagrams and the linked diagram theorem. And these are topics which we will try to cover today and also tomorrow. So what I'm going to do now is simply to switch to the whiteboard, and we will stay with the whiteboard for most of the time now. So the first thing which we will do is to remind ourselves a little bit about that exercise which we had last week. Or not exercise, but example. So that example was a simple Hamiltonian, which then gave us a two-level problem, which we could solve analytically, but we can also solve it exactly with Brane-Wigner perturbation theory, and then approximatively as a perturbative expansion in terms of Rayleigh-Schrödinger perturbation theory. And that example contains a lot of the basics of what is coming now, and also a lot of the basics of money-body perturbation theory. So if you get a feeling and understanding of that example, you have the basic essence. So let me quickly remind you of what we did last Friday. So we introduced a Hamiltonian which contained two elements, and since we only have two levels, and we can think of this as a one-body problem or single particle problem. And we had a one-body operator, and this was multiplied with the quantity epsilon I, which we interpret as a single particle energy. And then we had an interaction piece, which actually gives us the non-diagonal matrix elements. And we had a sum over I different from J. So this is a double sum, and they run from 1 up to 2. And we had an AI dagger and AJ here. What we did then was to set up the Hamiltonian matrix. So I'm just quickly reminding you of these quantities. We are also assuming that, as before, that this term which you see here is a term which we could label as an H0. And this term which you see here is the one which we would typically call for the interaction term. And we're also assuming that there is a basis, H, which is an eigenbasis of H0. So we have an H0 multiplied with a phi 1, which is given by an epsilon 1 times phi 1. And we assume also that this phi 1 is now given by an A1 dagger acting on the true vacuum. And similarly, we had a state, this is a second state, which is given by an epsilon 2 times phi 2 here. And this, again, this state phi 2 is then in second quantization is given by an creation operator A2 dagger acting on the true vacuum state. And then we could calculate so-called matrix elements. And the typical matrix elements which we would get then would be something like a phi 1 of H of phi 1, and we found that one to be equal to epsilon 1. Similarly, we had a phi 1 of H of phi 2, which was simply equal to this parameter lambda. And then we had a phi 2 of H of phi 2, which was simply equal to this epsilon 2 energy. And then we could easily set up the Hamiltonian matrix, and we can diagonalize the whole problem. So when we did that, we got the following Hamiltonian matrix, which we want to diagonalize. So the matrix we end up with is an epsilon 1 minus an energy E1, and then we have a lambda, and then we have a lambda here, and then we have an epsilon 2 minus E1, if we are focusing on that eigenvalue. And if we want the next eigenvalue, we have an E2. So this system which we are looking at is a system where we have defined the E1 state to be the one which is the lowest one, and this is a two-level system. And typically what you will see when you set this up, depending on the strength of the interaction and the sign of the interaction term, which is this lambda, you could then have something where you start with an epsilon 1 and an epsilon 2 here, where you then either get a spread, or depending on the sign of the interaction, you can get a spread or you can get a shrinkage. So when we did Brane-Wigner perturbation theory, what we found then was that the energy delta E1, this correlation energy, which we define to be E1 minus epsilon 1, this was given by lambda squared of E1 minus epsilon 2, which means again that we ended up with the same equation which we would get when we write out the determinant, which we have here. So if we just write out that determinant, what we get then when I multiply here with epsilon E1 minus epsilon 2, I multiply up here and I subtract lambda 0, what we see then is that this delta E1 multiplied with this quantity E1, 2, this translates into E1 minus epsilon 1. So I multiply up epsilon 1 minus E1 minus epsilon 2, and then subtract lambda 0. lambda squared, then I get 0 here. And this is the same as the equation for the characteristic polynomial when I now write out the determinant. So Bruyère-Wigner perturbation theory stops at second order for this specific example, whereas when we now do Rayleigh-Schrödinger perturbation theory, we have to set up a perturbative expansion. So let's now look at Rayleigh-Schrödinger perturbation theory. This is roughly where we ended last week. So the first 2 pages which we have seen here is mainly a repetition of the example from last week. So let's now move to Rayleigh-Schrödinger perturbation theory. And the thing we did last time was to look at Rayleigh-Schrödinger perturbation theory to third order. So let's do that. This is a quick reminder of what we did. And in Rayleigh-Schrödinger perturbation theory, E1 is replaced by epsilon 1. And the same happens if we are going to look at the state E2, that is replaced by epsilon 2 here, which are the non-interacting energies, which we know. So when we did Rayleigh-Schrödinger perturbation theory, then this correlation energy for the lowest lying state, now I'm writing RS PT, Rayleigh-Schrödinger perturbation theory, that was given by a phi 1 of H. And now we have to be a little bit careful because Rayleigh-Schrödinger perturbation theory is expressed in terms of the interaction. And in our case, this term was exactly equal to 0. And now I have a second order term, which we have discussed several times. And this is divided by epsilon 1 minus epsilon 2 here. And finally, the third order term runs like a phi I of HI of phi 2 here. And then I have a phi 2 of HI phi 2. And what we found last time is that this term to third order here, the first one, is actually equal to 0 because we don't have an interaction which gives something different from 0 for these terms, which are the diagonal ones. So if you go back to the Hamiltonian matrix, we have defined it so that these matrix elements, like the phi 1 and phi 2, is only given by the non-interacting part. So the only piece which gives us a non-zero contribution when we look at the transition from phi 2 to phi 1 is now given by the interaction piece which we have here. Then we have a denominator here which goes like epsilon 1 minus epsilon 2 squared. And finally, we have this term which we will discuss in more detail later today. So this contains a phi 1 multiplied with a phi 1 HI of phi 2 here of HI of phi 1. And this is then divided by epsilon 1 minus epsilon 2 squared. Now, in both of these terms, the interaction piece, which connects the same states, is equal to 0. So that means that this one is equal to 0. And then this one is also equal to 0. So that means that we end up with a contribution to third order, which is exactly equal to 0. So to third order perturbation theory, when I'm summing up everything, this is going to give me lambda squared divided by epsilon 1 minus epsilon 2. And if I compare that with Bruyère-Wigner perturbation theory, what I found then, so this is BWPT here, that was given by lambda squared divided by epsilon 1 minus epsilon 2 here. So this is roughly where we ended last time. And one of the things which we did as well was to look at the diagonalization problem, and we performed a Taylor expansion of the lowest lying state. So when we diagonalize the problem, we can then perform a Taylor expansion. eigenvalues. Value problem. And since this is a 2 by 2 matrix, it just gives us a second order problem. And that means that what we end up with is for the lowest lying state, we have the solution, the exact solution, which is given by 1/2. And we have an epsilon1 plus an epsilon2. And then we have the minus sign because we are looking at the lowest lying state. And we have an epsilon2 minus an epsilon1 here. And this is multiplied by the square root of 1 plus, and then I have a 4, and I have a lambda divided by epsilon 1 minus epsilon 2, sorry, minus epsilon 1. And this is squared, and this is also squared. Then what we did was to perform a Taylor expansion, and we've also made the assumption that epsilon 2 minus epsilon 1 is different from 0. There's also a very important aspect when you're doing this Taylor expansion. If this is going to converge, there is a requirement, obviously, on lambda, or epsilon 2 minus epsilon 1, and its absolute value being less than 1. So if we then Taylor expand this quantity, what we got then, when we looked at the energy E1 minus epsilon 1, which is the delta E1, when we Taylor expand the root, the square root, we get this one to be equal to epsilon 1. And then I have a term plus, so sorry, not epsilon 1 here because I shifted that over. I get lambda squared divided by epsilon 1 minus epsilon 2 here. And then I have a new term which runs like minus lambda to the power of 4, which indicates that we should expect a non-zero contribution from a fourth order in Rayleigh-Schrödinger perturbation theory. And this goes on like that. Now, if we compare that with the Rayleigh, if we compare this expansion with the Breuer-Wigner perturbation theory, if we go back to that expression, so this is now us just Taylor expanding, and we recognize this term here, which was second order perturbation theory, which we found here. And we will later see today that this one corresponds to fourth order perturbation theory. So we had no terms to third order, which is this one. And we see here that we have the interaction to fourth order. So this seems to indicate that there is going to be a fourth order term in Rayleigh-Schrödinger perturbation theory. So if we now link this with the Breuer-Wigner perturbation theory, when we take delta E1 of the Breuer-Wigner perturbation theory, what we have then is a lambda squared divided by E1 minus epsilon 2 here. And this is something which we obviously can rewrite by adding and subtracting epsilon 1. This is nothing but lambda squared divided by epsilon 1 minus epsilon 2 plus delta E1 for Breuer-Wigner perturbation theory. So I'm skipping this BWPT in here because these are the same terms here. So what I obviously can do now is to perform a new perturbative expansion. I can pull out a term lambda squared divided by epsilon 1 minus epsilon 2 here. So I can actually rewrite this as a lambda squared of epsilon 1 minus epsilon 2. And then I have a 1 minus, and then I have a delta E1 divided by epsilon 1 minus epsilon 2. So I'm performing a new Taylor expansion where my term, which I expand around, is delta E1 divided by epsilon 1 minus epsilon 2. And then I get a plus, and then I have a delta E1 divided by epsilon 1 minus epsilon 2 squared. And this just continues to infinite order. And then I can regroup this one by simply inserting again the expression for delta E1. So I can regroup these expressions. And that means that what I get then is lambda squared divided by epsilon 1 minus epsilon 2. And then I get a 1 minus lambda squared divided by epsilon 1 minus epsilon 2. And this is squared, plus, 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 etc. So this is just a rewriting of the same equation. And obviously, since Brane-Wigner perturbation theory gave us the exact result, clearly when I perform a perturbative expansion, I should get the same result, which I got by performing this Taylor expansion of the square root. So essentially everything here fits. So what we see now is that the Brane-Wigner perturbation theory gives us only, due to the choice of Hamiltonian, terms to second order. And all higher order terms will obviously contain terms where we go from the same state to the same state. And they are by construction equal to 0. So we can easily see that the fourth order, fifth order, sixth order, and seventh, etc., order terms, they disappear. Brane-Wigner perturbation theory gives the same result as the exact solution when we diagonalize that matrix. And if we Taylor expand Brane-Wigner perturbation theory, or the exact one, we're actually getting terms by terms which we would recover from Rayleigh-Schrödinger perturbation theory. So let's, as a small exercise now, look at Rayleigh-Schrödinger perturbation theory to fourth order. And then when we are done with this example, we are going to go into more a diagrammatic discussion. And we are going to come back to this simple example and see what these terms may mean from a diagrammatic point of view. But what we're going to do now first is just a technical exercise where we are going to calculate the terms to fourth order in Rayleigh-Schrödinger perturbation theory. So let's look at the delta E1 in Rayleigh-Schrödinger perturbation theory to fourth order. So this is Rs PT. Now what we have in Rayleigh-Schrödinger perturbation theory is then a term, and I'm going to use a more compact expression here because we're going to get 5 different terms. So I'm going to use the notation that if you see this HI here, this is now going to stand for 5 ones because this is the ground state we are looking at. So this is a ground state expectation value with the Hamiltonian HI. So this is just a shorthand notation which I'm going to use here. Similarly, if you see something like HI multiplied with this operator Q divided by an operator E0, which I'm going to define pretty soon, this one is the same as phi 1, which is this ansatz for the ground state, HI of Q of E0 of HI. So this is actually second order perturbation theory. And Q now is simply defined by this state phi 2. And this E0 is simply epsilon 1 minus H0. So we need to put hats on all the operators here. So with this minor introduction of notations, we can then write down the expression for many-body perturbation theory with Rayleigh-Schrödinger perturbation theory to fourth order. And the term then is equal, so this is equal to H1 of Q, HI, sorry, H0 of HI of Q of E0 of HI of Q of E0 of HI. So you see this is a fourth order term. And the different terms here stand for a phi 1 to phi 1 expectation value. Then we have a minus sign, and I have a term, HI of Q of E0. But then in between here, I have a term which is HI, the expectation value, which is the same as this term here. Then this is multiplied with Q of E0 of HI times Q of E0. And then I have a new HI term. So I should put hats everywhere here. If I forget it, please forgive me for that. So these are all operators. And I have 3 more terms. So let's write out all the terms. So this is just based on a regrouping of the expansion of the expression for the correlation energy in terms of the delta E1, the correlation energy itself. So we regroup everything in terms of the interaction to a given order. So we get a minus, an HI, and then I have a Q of E0, HI of Q of E0, and then I have a expectation value here, HI, Q of E0 of HI. There is a new term plus an HI of Q of E0 of HI, and then I have a Q of E0, and this is now multiplied with a new HI, and then there's a Q of E0 of HI. So when you look at these different terms here, and then we need to add the final one, which is simply an HI of Q of E0, but this has a second order term in here. So this is Q of E0 of HI of Q of E0 of HI. And let's put hats on everything so we are consistent. Now, the interesting thing with these expressions and the Hamiltonian which we have chosen is that there is only one term which survives. So let's see that after we've put hats on everything. So if you now look a little bit more carefully at these expressions, we know that from the simple model which we made, this term here has to be 0. This term here is equal to 0. The same applies with that one. Now, in this case, however, this term here is actually second order perturbation theory, which is non-zero. And here I would actually, if I look at these contributions here, what I'm going to get, if you think of this as second order perturbation theory, there's going to be a lambda squared divided by epsilon 1 minus epsilon 2. If I take these two terms, what this is actually Q0 divided by E0 squared, but Q squared is equal to Q. So this is the same as Q divided by E0 squared. So that becomes equal to phi 2 of phi 2 divided by this epsilon 1 minus H0 squared. So that means that I'm going, since I have only one intermediate state here, I'm going simply to have a term here when I put in everything, which is just equal to epsilon 1 minus epsilon 2 squared. And then I have the interaction piece, which is simply given by this term lambda. So this fifth term, which you see here, the last one, is going to give us in total. So if we take the whole term, I'm going to get minus lambda squared, lambda to the power of 4, divided by epsilon 1 minus epsilon 2 cubed. So if we now look at this term here and go back to the previous page, so what we said is now that this term here is 0. This one is obviously 0 by construction and definition of the Hamiltonian. If I then look a little bit closer, you will also see that this term has to give 0. And in the calculation of the intermediate states here, I'm going to have phi 2 going to phi 2, which also gives us 0. So this term here is going to give me 0. So that means that the only term which survives is the one which comes from the last term here. So if you look at this expression here, what we have now is something which looks like exactly what we have here. This term times that. So what you will see then when you do this Taylor expansion and you go to higher order terms, there will be only terms with even powers of lambda. So there will be a term to sixth order in the Rayleigh-Schrödinger perturbation theory. So if we do that, we will actually get a term then which matches exactly the one we got from the Taylor expansion. So what we see now is that Rayleigh-Schrödinger perturbation theory, if we want to think of this in terms of Taylor expansion as a mathematical tool, Rayleigh-Schrödinger perturbation theory is nothing but a Taylor expansion around a specific energy and a specific interaction strength. So what we made is actually a perturbation expansion, or a Taylor expansion, to be more correct, around lambda divided by epsilon1 minus epsilon2. And clearly, this tells us from this simplified model, we can actually generalize this to the more general cases. And you see that when we do the Taylor expansion, there is obviously an important constraint, which is now defined in terms of the ratio of the interaction strength and the non-interacting energies which we are studying. So if this is less than 1, then obviously this Taylor expansion will converge, and we can use many-body perturbation theory, and hopefully higher and higher order terms vanish or become very small, which means that we can then simply truncate our many-body perturbation expansion at a given level in perturbation theory. And typically, it's very seldom that you venture beyond the fourth order, because if you have many single particle states, this is going to give rise to extremely many contributions. Now, I hope the simplicity of this model shows some of the basic features of many-body perturbation theory. What we are going to do now, but please feel free if you have questions, just put them in the chat here, or unmute yourself and just ask questions if something is unclear. What we are going to do now is to look in more detail into a diagrammatic representation of these terms. So what we've done now is just the algebraic expansion. At the end, you will obviously end up doing that. But the diagrammatic expansion is very powerful, and we will use that when we move into other many-body methods like copper cluster theory next week, and also towards the end of the semester when we are going to scratch the surface of Green's functional theory. So the diagrammatic representation is something which gives us a very powerful tool to analyze the different contributions. And often we can give many of these diagrammatic representations a kind of a physical meaning. So what we are going to do now, going back to second order, which is the terms which we discussed last week, we are going to look at this in two different ways. One, where we are going to represent everything in terms of the new vacuum state, and two, where we are going to represent everything in terms of the true vacuum. And hopefully that is something which can give us a little bit, has a more intuitive understanding of the particle hole diagrams which we get, compared with those which we would get if we just deal with a true vacuum state. So let's now look at the diagram rules, and we are going to cover different topics. So this is just diagrams and diagram rules. It's a very powerful tool because we can actually, by looking at a diagram, we can write down contributions to many-body theory immediately. And as I said, we can assign to some of them some kind of physical meaning. So let's go back and start with the example of second-order perturbation theory, which we elaborated the last 2 weeks. So we had a delta E, and we put this 0, and this is to second order. And this is something which we now wrote as a phi 0, which is our ansatz for the ground state. We have this interaction piece, we have the excluded space, and we have this term E0 multiplied with HI, and this is given by phi 0. And let me just quickly repeat. So this Q now is a sum from I larger than 0 of all these orthogonal. So this, sorry, this was not my letter I. So this is my attempt at the letter I. The term E0, which we have here, is simply our unperturbed or non-interacting energy minus H0, the operator. And then we have defined this H0 acting on this basis to simply be given by this uppercase letter epsilon acting on the states phi of I. So this is an orthogonal basis and it's an eigenbasis as before. So let's now, instead of using that notation where we had states I, J, K, L, etc., which are states below the Fermi level, and then we have the A, B, C, D, which are states above the Fermi level, I'm going now to try to link this diagrammatic representation and the diagram rules in both the true vacuum representation and in the representation of the particle hole modified vacuum state. So if we now look at a specific Slater determinant, what we could think of now is a specific state which is defined by a given number of hole states and a given number of particle states. So if I look at the determinant which I could label as a 1 here, so this is 1, we could think of that one as a creation operator for particle state P1. And then what I'm going to have then is a set of states where I now have removed one hole state. So I would have a hole state H2 here. So I'm writing this now in terms of the true vacuum. And this will be an H of N dagger acting on a true vacuum state. And if we are thinking of this as a particle hole excitation, we could now have this one as an AP1, and then I have the hole state, which I have removed, acting on the vacuum state phi 0, where this phi 0 is defined as before in terms of all the the states below the Fermi level. So this goes up to the Fermi level, and I'm simply indicating this by an H of I acting on the true vacuum state. So that means that I could now think of a new state, phi 2, which could now be given by this H1, and then I have removed a hole state 2 here. So I create a particle state, and then I have my H3, and this goes all the way to up to H of N, the number of particles acting on 0. And this is what we would, in the particle hole representation, write as an AP2 of an AH2 acting on phi 0. Okay, so these are just representations which we are going to use now. And we could now think of this, if we look at the way we have done things before, you could think of this as having the Fermi level. We have a state H1, H2, and this is given by all states up to Hn. And then I have now a particle state 1, I have a particle state 2 above the Fermi level, and etc. And this can go on to infinity. So the contractions which we have defined are the same as before, so we're not going to repeat them. And if I now look at the contribution to many-body perturbation theory, So let's now look more closely at the contribution to second order. And now we are taking a Slater determinant, which is given by all the whole states or the states below the Fermi level. So if I'm now representing this state phi 0 in a diagrammatic way, we could now think of this one in terms of all these lines, H2 up to an H of n here. And you see clearly why we want to skip the standard particle representation, because that is going to give us many, many different terms. But if I now look at this term in second order perturbation theory and try to write this in a diagrammatic representation, what I will be getting is now obviously a sum over all these intermediate states. So I'm going to have these states I larger than 0. I'm going to have a Slater determinant here, which represents my whole states. And I'm just going to write this in terms of dots. And then what I'm going to get now, due to the interaction term, I'm going to get one term here. So this is going to be my state. So this is the interaction which we have here. And I'm going to mark the particle states with these bars. So this is just a particle state, pi, no, not pi, but a p and p prime here. And this has additional whole states which are not interacting. So what you see here is actually the state phi of I. And then above here, I have the final state, which is just my phi 0. This is then multiplied with the denominator. So this is the whole contribution. So we have an epsilon 0 minus the energy of the intermediate state, epsilon I. This is further multiplied with the state, which we call phi of I. This is the many-body state, which we then label like this. And then we have a particle states here. So this is my interaction term. So I have the two intermediate particle states. So this is one possible contribution. And then this continues to the final state. And before the interaction, what we had is just the state phi 0 here. So one contribution which we could get, if we now look at this specific contraction which we have. So if we take a contraction here, one of the possibilities is that if we now insist on writing this in the true vacuum representation, what I would get then when I perform the contractions is a sum over two particle states, Pn and Pn. And then I have all these whole states which I'm setting up. I have an H1, I have an H2 here. And this goes on all the way to this term here now, because now I'm bringing together this term with that term. And I'm indicating the two particle states, the states above the Fermi level here, with a Pm. And then I have a Pn here. And in here, I have just a whole state. It could be an HK and an HL. And I end up with an HK and HL here. So this is just one specific contribution. And then this continues up here till the final whole state HN. And you see why we normally prefer to write this in a kind of a particle hole representation, because if we're going to keep track of all these single particle hole lines, this is going to give us a pretty unwieldy diagrams. Okay, I see now that we have gone on for some 45 minutes. So let's take a small break, and feel free to ask questions during the break, or if you wish to do something else. So what we're going to do now is to obviously move away from this particle-particle formalism, which we use in connection with the true vacuum, and then they just link this with the particle Hall formulation. One of the reasons why we're doing this is that we need to discuss quantities like unlinked diagrams, which will come pretty soon, and also something which is called polyviolating diagrams. Now, if we look a little bit at this contribution here, one thing which we did not include is the summation over the Hall states. So we have now just singled out a specific Hall state here, and then we are running the calculations over all possible particle states. If we want to depict this in a slightly different way, the way we can set this up is as follows. So we have a state phi 0, which we want to end in. And this is in the particle formalism. This is simply given by all these single particle lines like this. Then I have an interaction piece here, h of I. And this interaction piece is something which we will simply write in terms of either this term or this term here, which can represent a one-body operator, and we just leave that one-body operator unspecified. Then we have the intermediate states, which are represented by the operator Q. So this is an I here. So we have a phi of I divided by this epsilon 0 minus epsilon of I. And the way we can depict this one is something like a collection of these different lines. And then we had these two particle states. It doesn't need to be two particle states. It could be one, it could be many. And I see that there's a question. Okay, and then we have the remaining states. And all these ones have to be contracted. So then we have a interaction piece here. So I leave this one without lines, or without arrows, sorry. And then I have a phi 0 here, which then is again rewritten in terms of all these single lines here. And all the terms which we have here, they have to be contracted. So when we are setting up this kind of contribution, we end up with something which could look like this in a diagrammatic form. So let's just take a look at a possible state which we have. So we could have a diagram in the particle formalism, which looks like this. So we have an H1, H2, and then we get a term here where we have a particle state P, which we just label as a Pi, and then we have a Pj here. There is an interaction piece. There is a new interaction piece here. And now we could think of whole state Hi and whole state Hj. And then we have a Hi and Hj leaving. And then we have all the remaining states below the Fermi level, up to H of n. Now, this is a contribution which we would, in the particle Hall formalism, we would now simply bring together the two Hall lines here, and we skip all those Hall states which do not interact. So this diagram which we see here is something which we, in the particle Hall formalism, would write, as we did before, as something like this. Now, if we keep this bars here to indicate that this is a particle state, so we would have now an H of I, an H of J, we have a P of I and a P of J, and this now has the sum over all the possible HI, HJ, and PI, PJ. And the way we have been labeling this one has been as a state I, which is a state below the Fermi level, a state A, which is a state above the Fermi level, and finally a state B and a state J below the Fermi level. And then we have a summation over AB, which are larger than F, and IJ, which are less or equal up to F. Now we could have an alternative contribution, which we also discussed last time. So let's now look at an alternative contribution or an additional contribution to these diagrams. So what we could have is something which looks like this. So we have an H of I, an H of 1, H of 2, and then we have a state here where we have an H of I and an H of I here. And we could now have an intermediate whole state, which I'm going to call for an H of K. And then I could have a particle state here, so which I can call for P of J. So this would now be an H of J here and an H of J. Sorry, this would be an H of I here, like that. And then I would now have the additional bystanding whole states, which I simply label as an H of N. Now, in the particle whole formalism, this would then translate into the following type of diagram, because now we have an ingoing whole line, an outgoing whole line, and we could translate this one if you now look at the intermediate state which we have here, this one. So this could now be a state which looks like this, or a diagram which looks like this, where we now have the particle whole intermediate excitation here, and then we would have this closed line because we are summing over the states H of I. This could be an H of I here, and then finally we would have an H of J in here and a P of J here. So that could be one possibility, but in principle, these initial states here and this initial final state here, they don't need to be the same. So in general, what we got last week is that this diagram, when we write it out in the particle whole formalism, would be something like this. We have a summation over state K. This is the general case. And then we have a particle whole state. And then we have an A, and we could have an J here, and then we have an I here. And this is the same when we now set up the diagrammatic expression in terms of an analytical expression. This was the same as a summation over A, I, J, K. And then I have a specific matrix element now, which is given by K. And then I would have the whole state J. I have an interaction piece. I have an incoming whole state K and an incoming particle state. And here I have a outgoing whole state I, an outgoing particle state A. I have a V, and then I have a state I and a state J here. And these are anti-symmetrized matrix elements. But then, since we have this energy denominator, if you now look at the expression which we put up here, it means that as in the intermediate state, we need to take into account this specific energy denominator here. So if you look at this intermediate state, what we can do now as a kind of rule is to just look at the particle whole states which we have here. So that will define this energy epsilon I. So in this specific case, the intermediate state has an energy which is given by epsilon A minus epsilon J minus or plus actually epsilon 0. So that means that this denominator is now going to be simply given by the sum over whole energies minus the sum over particle energies. So I'm just getting an epsilon j minus an epsilon a. So it means that when I look at this diagram, I can read off some specific analytic expressions. So you see now that we have a outgoing particle state to the left, K, whole state. I have an outgoing whole state J to the right, so that comes in here. I have an incoming whole state K and an incoming particle state A to the right, so that comes in there. Similarly here, I have an outgoing particle state, whole state I, an outgoing particle state A, and two incoming whole states I and J. And this represents one of the other contributions to many-body perturbation theory. Now, if I look at that specific diagram, which I considered here in the particle formalism, there are many, many other terms. So one possible term which we could get, which gives rise to a similar diagram like the one you have here, could be a diagram like the following. So I could now, if I stick to the particle formalism, I have the states Hi, H1, H2, and then I'm performing a contraction with the state Hi here. And then I have an intermediate particle state, which I label as a P of J. And then I have the interaction piece, and I have an interaction, a whole state Hj here, and a new whole state Hj, which leaves. And in this specific case, let me just be a little bit more careful here. So I have an H of J, and then I have my particle state, P of J. And then I can have a contraction with an additional whole state here, which I label as an H of K. And I have an H of K here. And this continues all the way up to the last bystanding whole state, or particle state in this case. If I look at this diagram is something which I could, in the particle whole formalism, I could rewrite this one by bringing together the whole lines here, and same with these two, and with these two, because they are now, we are now summing over all the whole states. So this diagram could look something like this. So if I insist on this labeling with Hi, I would here have an H of K, I would have a P of J, and an H of J here. This is the same when we now look at the notation which we've been using with A, B, C, D, I, J, and so on. This will be the same as this diagram here. This diagram is actually the same as the one which we drew earlier. It is topologically equivalent, because if you look at the matrix elements which are involved with interaction, we are actually going to get the same expression. So if we now look back at what we had here, we had a K, A, J, and I. So we would simply put a K, an A state, if we now want to be consistent with what we had, a state J here, and a state I. So if I look at now the expression for this specific diagram, this is going to be given by the same summation of A, and then I have I, J, K. I'm going to get a matrix element now with K here, as before, the outgoing whole line, a J here, and then I have a V, and then I have my incoming whole line, KA. And this is then multiplied with A, and then I have I, a V, and then I have J and I. The denominator is now simply given by the difference between the number of whole states and number of particle states, their energies. So that means that I'm going to get an epsilon I minus epsilon A. Now, if you look at this expression here, if you look at this first term here is the same as we have here, as you can see. However, the second term, we have interchanged A with I, and here we have interchanged J with I. However, we know that since these are antisymmetric matrix elements, this term which you have here is equivalent to the previous one. So what we say then is that these are topologically equivalent diagrams. We will see another contribution, which is also an example of a topological equivalent diagram. And so let's look at another contribution in the particle formalism first. So let's just draw the lines here. And then we have a contribution which looks like this in the particle-particle formalism. But then I have an exchange piece here. And then this continues all the way up to the last whole line, H1, H2, H of N. And in this particular case, what I'm having now is an H of I here, which is interchanged with an H of J. I have my PJ here, and have my HJ, and I have my H of I here, and I have also the intermediate state H of I. So this is again an intermediate particle Hall state. If I write this diagram in the particle Hall formalism, what I would get then, because then I skip all the bystanding whole lines which do not contribute, what I get then is a diagram which looks like as follows. So I have this state HI here, and then I have a interaction line. But then, since I'm doing the exchange here, I'm getting this whole line, HJ here. And then I have my particle line, which I just keep fixed. So this is a particle line, PJ. And I have my new interaction. And then I have this whole line, which is now given by H of I here. Now, in general, this does not, the state which we have here doesn't need to be an H of I. I could have had another state up here. So in general, what I'm going to get is a contribution which looks like this. I'm going to have a diagram when I write it out, and now I go back to the A, B, C, D, K notation. So this could be a state K, which I have here. I would have the interaction piece, and then I have the whole state J. Then I have my particle state of A, and then I have this piece here. So this is the way I would write this diagram in the particle Hall formalism. Now, if I look at this diagram here, what you will notice then, when you're now setting it up, is that without thinking of the sign here, so we would find that this term is now proportional to using anti-symmetrized matrix elements. So I have an A of I, J, K. Then I have a matrix element, K, and I have my incoming whole state, Kj. And then I have a V here, and I have my state K again, and A. This is then multiplied with a outgoing whole state I, and I have an outgoing particle state A. I have a V, and then what I have now is a whole state J, which is going in, and then I have a whole state I, which is also going in. And this is divided by epsilon I minus epsilon A again. Now, if you look back at what we have previously, You see now that I have a matrix element either with this one, which we found is equivalent mathematically to the diagram which you see here. You see that they have a matrix element which now goes like IA, Vj. So let's take a closer look at what we have here. So here, if we look at the vertex here, what we end up with is a matrix element which is IA, V, and if we go back, it is J and I. Whereas when we look at the previous case, what we had then is a matrix element which was given by IA of V, and then they had IJ. And we know that this matrix element is simply given by minus that matrix element. So when we are now using anti-symmetrized matrix elements, except for this minus sign, this diagram which you see here is something which we would call topologically equivalent with this diagram and this diagram here. So when we are setting up the final summations, you see now that every interaction vertex has a factor of 1 divided by 4, but what we end up with is just one term. So that means that in total, there are actually going to be 16 different types of contributions. And here we have listed this one, we have listed this one, and we have listed this one. And there are actually 13 more different possible permutations of these particle and whole lines which we can make. So another diagram which we could make would be a diagram which looks like this. And then we would have the particle state here, and then we would have the whole state here, and then we would have another whole state like this one. So then we would have an I here, an A, a J, and a K here. So all these diagrams, due to the fact that we are using anti-symmetrized matrix elements, are all going to be what we normally call topologically equivalent. So when we are going to set up the contributions to second order, we're actually going to look after diagrams, only those diagrams which are topologically equivalent. And of these one particle, one hole excitations, we can limit ourselves just to draw one of the diagrams. So of the one particle, one hole type of excitations to second order, what we can limit ourselves to is actually to just draw these diagrams here. And then when we want the contribution, it suffices to actually look at one of them and write down the analytical expression for the contribution to the energy. So this would be labeled with K, this would be an I, we would have a J and an A here. If we stick with that convention, if you prefer this convention with hole 1, hole 2, hole 3, etc., this is a notation which is equivalent to the one which we have chosen here. These are just different ways of labeling the same things. So we would then have just one contribution of the one particle, one hole when we draw the diagram. It's common when we now use these type of diagrams, which are called Feynman-Goldstone diagrams, that you would just draw only one of them, meaning then that the interaction vertices here are normally considered to be anti-symmetrized vertices. So if we look at the two-particle, two-hole excitation, which is the other contribution which we discussed, and that one is the one which we have had here. So let's just go back a little bit. This contribution here, we saw last week that we have 3 more diagrams where we then can change the two-particle lines, we can change the two hole lines, and then we can change both the hole lines and the particle lines. So at the end, what we see now is that we have a specific type of contributions to second order. So to second order, we can draw these diagrams in either the particle formalism, which is not very convenient. We would then end up with two contributions. And this contribution here is the one which represents a two-particle, two-hole excitation. And then we have the other one, which represents a one-particle, one-hole excitation. So we have reduced an intermediate state, which is given by an expectation value or transition probability of many body states, and we have reduced these to a representation in terms of single particle states. So we would have an AB and an IJ here. We would have a K here, an I here, a J, and an A here. Now, what you saw is that we, from these type of expressions, we start seeing a glimpse of what we might call the diagram rules. So let's now try to write them down and also give some additional rules, which will then allow us to set up the contribution to the energy at a given order by just looking at specific diagrams. So in this case here, there are in total 4 different diagrams. But since we're using anti-symmetrized matrix elements, we can just reduce it to looking at one contribution. And in this case here, we do actually have 16 different contributions. But they all reduce to just one contribution. So this will be what we call the topologically distinct diagrams to second order. So let's just write this down. In terms of diagram rules, so the first diagram rule is that we just draw all topologically distinct diagrams to a given order. And now we need to have some additional driving rules here. So what we mean by the topologically distinct diagrams, so let me just fetch my notes on that, just a moment. Just a small moment, I just need to scroll back and find my notes here. So this drawing all the topological distinct diagrams means now that what you do then is that you're linking of a given order by linking up particle and whole lines with various interaction vertices. And two diagrams can be made topologically equivalent by deformation of the fermion lines, obviously under the restriction that one, the ordering of the interactions is not altered, particle lines remain particle lines, and whole lines remain whole lines, and the ordering of a contribution at the initial stage and at the final stage is not altered. So we are going now to do that, to set this up by linking up particle and whole lines with different interaction vertices. Under the constraint or under the restriction, that one, the ordering of the interactions is not altered. And if you're doing time-dependent money-body theory or time-dependent perturbation theory, then you can think of, if we go back to the diagrams here, you could think of an interaction taking place at the time t1 here. And then something happens, you create a two-particle, two-hole state. And then this goes back to the ground state at the time t2. So this is a kind of a pictorial way of thinking of the physics of these type of interactions. But this ordering of these vertices here is not altered. That is an important restriction. So this, if you do the time ordering or time-dependent money-body perturbation theory, then you would say that the time ordering of the diagrams is not altered. But here, we would say the ordering of the interaction vertices is not altered. Is not altered. B, particle lines remain particle states. Particle states remain particles, remain as such. Because when we have performed the contractions and we have defined that specific state to be a state above the Fermi level, it should stay as a state above the Fermi level. And you would say that the same applies for whole states. And then the ordering at the beginning and at the end is not changed. So ordering of the interactions at the beginning. So if you're thinking of time and time-dependent perturbation theory, which we will not cover in this course, except when we start looking at Green's function theory, it means that you could now think of the interaction taking place at a time t0 in the beginning. And this t0 could be time back in infinite times. And then something happens in between. And then at a time t1 here, you have a final state which is being produced. And the system remains, for instance, in that state. So that means that the ordering of the interactions at the beginning and at the end, and at the end is unchanged. So that means that we have some specific rules in order to distinguish so-called topologically distinct diagrams. So we cannot alter hole lines, we cannot alter particle lines, and we cannot alter the ordering of the interactions. So each interaction vertex which we have is normally thought of either as a anti-symmetrized matrix elements, or it could be a one-body operator, or it could just be a non-anti-symmetrized matrix element. But normally we end up using anti-symmetrized matrix elements. So when you have n such interactions, you would typically then draw n interaction lines, and you would order these interactions in a specific way. So when we look at the explicit evaluation of each diagram, so for each of these topologically distinct diagrams, so for each topologically distinct, so topologically distinct means also that when I twist the particle and hole lines, I will always end up with a final expression which is the same. And this is very much dictated by the symmetries of the interaction or the integrals which you have baked in the evaluation of the specific contributions. So the explicit for each topologically distinct diagram, is, Then we are going to do the following. A, you would pull up the diagram. So if you're using Hugenholz diagrams, you would open up these dots, the dot vertices. For each diagram, you would set up interaction vertices. And these can be, if we're dealing with two-body interactions, they can be given by this type. We can also have a one-body interaction, which is like this, and we can have more complicated interactions. So we would need to set up the interaction vertices, and each of these vertices, each interaction contributes with an analytical expression for an integral, gives a specific expression, specific element. So if I'm having a generic state like this with P, Q, R, and S, this gives a contribution which runs like P, Q, or V, R, S. And this can be anti-symmetrized or not. Or alternatively, we could have a term like this one, where we just label this as an operator, and this has a state P and a state Q. So this would be a P, and then an integral defined by this specific operator. Then, if we now look at each of these diagrams, there is the following, which we have to pay attention to. And I'm coming back to the derivation of these factors. So there is a part C here. There is a factor which runs like -1 to the power of number of whole lines plus number of loops. So NL is the number of closed loops. And NH is equal to the number of whole lines. And I'm coming back to the demonstration of why we get such a factor. But now I just wanted to state the diagram rules. Then, for each interval, between two successive vertices, we have a term which we have to multiply with the diagram. So we would simply have a term here which now collects the whole states. So we would have a loop over the possible whole states, epsilon I here, minus the number of particle states, epsilon A. So if we now look at that specific term here, you can see that this arises if you go back to the diagram which we drew in the previous lecture. If you look back a little bit to this process here, and this is a second order process, you see now that this intermediate operator, which contains this intermediate many-body states, divided by the difference in the intermediate many-body non-interacting energies with the non-interacting energy of the ansatz for the ground state, then this translates, since epsilon I here contains also epsilon 0, plus minus the particle states which have been added and the whole states which have been subtracted, you so know that in this specific case, like this one, we have now a one particle, one hole excitation. The energy of the intermediate state is given by this contribution. But since we are subtracting epsilon zero, we are then simply left with the hole lines, because this denominator which we have here is actually given by epsilon zero minus the intermediate state, the one particle, one hole state. So this means that we have an epsilon A minus epsilon J, and then this comes with a minus epsilon zero. And you see that this translates immediately into epsilon J minus epsilon A, where the lowercase letter is the same as the single particle energy. So the intermediate states here, each one between a given vertex, gives us now a energy denominator contribution, which is simply the sum over the whole state energies, and subtracted from that one, the sum over the single particle state energies. So we have such a denominator, which we need to take into account. Then there is an additional rule, which we are going to set up here. So there's a rule C here. No, sorry, E, which says that there is a factor, and we are going to derive that one a little bit later. So there is a factor of 1/2 to the power of the number of equivalent lines or pairs which start at the same vertex and end at the same vertex. So this NEP here is the number of equivalent pairs of lines, and this can be whole lines or particle lines, lines which start and end at the same vertex. Then the final one, F, is to sum freely over all intermediate particle and hole states. Sum freely over all intermediate states. And these intermediate states are normally single particle and single hole states. Remember again that we can do this because we have assumed that a many-body state based on single particle states is a good answer for the system. If it is not, then this single particle states, which we are summing over, the intermediate ones, this is not applicable. So let's look at a specific contribution now. And let's be a little bit more ambitious and look at a diagram to third order perturbation theory. So let's look at examples of these rules, and then we're coming back to them, and we're going to look at how we can derive the rule for the phase factor, the number of hole lines, and the number of loops, and also how we can get this factor of 1/2 for each equivalent pair. So let's look at a diagram to third order and how we can express from just drawing a diagram. And this is the strength of the diagrammatic expression. So if you can draw all topological equivalent diagram, or you can have a program which deals with graph theories and finds all the topologically distinct contributions for you, then you can simply, from these contributions, you can set up the analytical expression which you need to evaluate at the end. So the first thing we do now is to put labels. So we have a label A for the particle states, B and C here. We have a label I here, we have a label J, and a label K. Now, if we go back to the rules, we are going to sum freely over all the intermediate states. So that means that there is going to be a sum over A, B, C, and I, J, K. So that was the last point. Let's now look at the number of equivalent pairs. So in this specific case, what you see is that we don't have, like here, A and C, they start at the same vertex, but A ends here at the final one, whereas C ends there. So A and C are not equivalent pairs. I and K are also not equivalent pairs. And you see also that the B and J and C here, B and C, or B and A, and J and I and J and K cannot be equivalent pairs. So there is no factor 1/2 to the power of equivalent pairs. Then let's now look at the number of whole lines and the number of closed loops. And then we will come back to the derivation of that. So what we see now is that we have 1, 2, 3 whole lines. So that gives us -1 to the power of 3, which is -1. Then we have one loop here. This is a closed loop. And we are going to come back to how we define a closed loop. This is defined as a closed loop, and this becomes also a closed loop. So this contribution here comes with a plus. And now let's set up the energy denominators. So if you now look at the energy denominator here, we are now going to look at the single particle states which we have between each interaction vertex. So that means that we are going now to look at the whole lines here and the whole lines here. So if we do that, we are going to get two energy denominators, and it's going to be an epsilon I plus an epsilon K minus an epsilon A minus an epsilon C. And then we have the next one, which is now given by an epsilon. So the next whole line is epsilon I plus epsilon J minus epsilon A minus epsilon B. And then, to end today's lecture, we are now going to set up the specific elements. So we have this expression here now, which we are dealing with. We are dealing with a two-body interaction, as you can see from here, from the vertices. So that means that if we start from the top, we have an outgoing whole state I, we have an outgoing whole state J, we have a V, and we have two incoming particle states. These matrix elements are anti-symmetrized now. And if we go to the next vertex, we have an outgoing whole state B. We have an outgoing, I have an outgoing particle state B, an outgoing whole state K. I have an incoming whole state J, and an incoming particle state C. And in the final one, I have two outgoing particle states of V, and then I have an I of K. So this will be the contribution to second order perturbation theory for that specific diagram. And this is one of many contributions to second order perturbation theory. Tomorrow, we are going to look at more examples, and we are going to look at the rules for finding the number of the whole lines and loops, and understand why we get these factors of -1 for each whole line. And then we're also going to look at the derivation of the number of equivalent pairs. And when we're done with that, we're going to look at something which appears in Rayleigh-Schrödinger perturbation theory and also in copper cluster theory, which is link diagrams. And then we will also have unlinked diagrams. And we're going to look at something which is called the link diagram theorem. And we'll also have another oddity which pops up, which is called Pauli exclusion principle violating diagrams. And with those elements, we have essentially a recipe by which we can draw and set up all contributions to a given order in many-body perturbation theory. So the way you would interpret, just to finish today, this diagram here is that we act on the vacuum state with a two-body interaction. We produce a two-particle, two-hole excitation, which is this state here. Then one of the particle-hole pairs, this one, does not interact with another particle-hole pair. So we have, in this case, we have the particle-hole pair CK, which gets modified to a particle hole per Bj. So you will say that this represents a one particle, one hole excitation. And at the end, we de-excite the system and we get back to the ground state, and we have a two particle, two hole intermediate state here, which gets de-excited through the operation of the Hamiltonian and brings us back to the ground state. So this is the way we would read this diagram here. Now, tomorrow we are going to look at more examples, and we also need to discuss in more detail some particularities which pertain to the evaluation of diagrams. And this is where we would stop today.